In our second example here of specific heat, it says that 1 gram of propane is burned in water, raising the temperature of the water from 20 to 25 degrees Celsius. In a separate experiment, 3 grams of butane. So notice it's not the same thing. It's propane and butane. They're both burned in water, raising the temperature of the water from 25 to 30. So one of the things they're trying to do with you here is they're trying to make you think, well, wait a minute. One's only going from 20 to 25. The other one's going from 25 to 30. Does that matter? And the answer is no, it does not. Okay, the temperature change on both of them, delta T, is still going to be 5 degrees. Okay, again, whether Celsius or Kelvin, it doesn't matter. Okay, the specific heat of water is the same. So again, think about Q equals MC delta T. The temperature change is the same. The specific heat of water is the same. The only thing that's different is the masses. Okay, 3 grams of butane makes the water go up by 5 degrees. 1 gram of propane makes the water go up by 5 degrees. So therefore, 1 gram of butane, if we look at our 3 grams of butane here, 1 gram of butane would only make the temperature go up by about a third of 5 degrees, so about 1.67 degrees. So therefore, 1 gram of propane releases more heat than 1 gram of butane does. Okay, so the combustion of 1 gram of propane releases more energy than the combustion of 1 gram of butane. That is correct. Okay, because again, 1 gram of propane raises the temperature 5 degrees of water, and 3 grams of butane also does the same thing. So 1 gram produces more heat of propane. Okay, and so what does this example show us? It shows us that the greater the mass, when the specific heat and the temperature are the same, then the greater the amount of heat transferred. Okay, example 3 says, and again, they're kind of introducing some new terms here that we haven't quite gotten to yet. Don't worry about what heat of vaporization is. Basically, it just means how much heat does it take to vaporize something. So, for example, nitrogen, it takes 5.6 kilojoules for every 1 mole. That's what this means here. For every 1 mole of nitrogen. So part A says, which sample, 2 moles of N2, so this one, or 10 moles of Z, requires the greatest amount of energy to vaporize at its boiling point? Justify your answer using the information in the table. So, again, these kilojoules per mole, that's kilojoules per 1 mole. So if you have 2 moles of nitrogen, you'd have to multiply that by 2. That equals 11.2. And then Z, if you have 10 moles of Z, you've got to multiply that by 10. That equals 17. Okay, so which sample requires the greatest amount of energy to vaporize? Absolutely Z would. Okay, and again, how would you justify that? Simply by saying that Z would require 17 kilojoules of heat, whereas nitrogen would only require 11.2. Okay, part B, which substance, N2 or Z, has the stronger attractions among its particles? Justify your answer using information in the table. Well, here we can just come back to this part. You certainly can use the heat of vaporization, where if you have a mole of each, certainly it takes more energy for nitrogen to vaporize than it does for Z. So therefore, the interaction, the intermolecular attractions between its molecules must be stronger. Or you can simply say that nitrogen has the higher boiling point, so certainly it's nitrogen. Nitrogen with its higher boiling point, therefore must have stronger intermolecular attractions between its particles. Okay, and then example 4 says, when preparing a solution of sodium hydroxide, a student notices that the temperature increases when dissolving NaOH in water. So if you take some powdered NaOH and you put it into some water, so we're going to take some powdered NaOH and we're going to put it into this water, the temperature will absolutely go up, okay? And that is an exothermic process. Okay, so in a separate experiment, the student dissolves 1 mole of sodium hydroxide in 1,000 grams of 2 different solvents. One of them's water, the other one is solvent X. So again, we got one where you're putting it into X, or into water, excuse me, and then the other one you're putting it into this substance X. Assuming the magnitude of the, and again, we haven't talked about this yet, but basically the heat is the same. So we know the Q value is the same. Would the temperature change in X be greater than, less than, or equal to the temperature change in water? So again, think about Q equals mc delta T. If the magnitude of the enthalpy change, again, which is this for now, is the same, and you're taking 1 mole of NaOH, so that is also the same, then again, now it's just down to the specific heat and the temperature change. Okay? If this number is going to be the same for both, and X has the lower specific heat, the lower the specific heat, remember, just like iron and water, iron has the lower specific heat, so its temperature change is greater. Water, with its higher specific heat, is not going to, its temperature change is not going to be as great. So therefore, X, again, the question, assume the magnitude, would the temperature change in X be greater than, less than, or equal to the temperature change in water? It absolutely would be greater than. Okay, so greater than. Okay, and because, again, all you would have to say is that since X does have the smaller specific heat, therefore its temperature change would be greater, which is, again, they tell you here, is consistent with the equation Q equals mc delta T. Okay, now we're going to go ahead and stop right there for now.